Hello, this is Professor Kuehn. Welcome back to my lectures on space, time, and motion. We are talking about Einstein's theory of special relativity. Specifically, we're focusing on the phenomenon of relativistic length contraction. You might remember in my previous lecture, we talked about how the length of an object, such as a train, is measured by different observers. One of the observers we considered was an observer riding on the train. The other observer would be one who's watching the train rush past at a high speed. And we came to the conclusion that these two observers are going to measure different lengths of the train. So, let me remind you of the situation. I'll draw a picture. Once again, we had someone standing on the train, and he measured the length of the train, and we will call that length L naught for the moment. And how does he measure the length of the train? He used what we called method 1, where he simply laid down a measuring rod or several measuring rods that were at rest relative to the train and counted how many of them fit. This is a standard way to measure the length of an object. You lay down some kind of ruler or meter stick across the object that's at rest compared to the object, and that's how you measure the length. The other person watches a train rushing past. This person times the interval between when the front of the train passes him and when the back of the train passes him. And by timing it and knowing the speed of the train, this person is able to once again measure the length of the train. And according to this person, the length of the train is L. And we found that there's a relationship between these two measurements. They're not the same. L was equal to L naught over gamma. This is the formula for relativistic length contraction. Let me remind you the definitions of these particular terms that appear in this formula. So first of all, L naught, that was equal to the length of the object as measured by an observer who sits at rest or is at rest with respect to the object being measured. That is the length of an object as measured by an observer who is at rest with respect to the object being measured. In our example, if I remember the names correctly, this was Luke who was riding on the train. He would be the one who would be measuring L naught. This is sometimes, by the way, called the proper length of the object. Don't get me wrong, that doesn't mean the correct length as if there's a preferred reference frame, but it's simply called the proper length. What is L in this example? L is the length of the same object as measured by an observer in motion compared to the other observer. The other meaning the first observer we just mentioned. Okay, and once again, gamma, this is that gamma factor that shows up time and time again in Einstein's theory of special relativity. It is simply a factor that relates the relative speed of the observers, v, and the speed of light. And remember, this is always greater than or equal to 1. It would be equal to 1 when the velocity is 0. That is when they're at rest compared to one another. And it blows up, that is, it becomes infinite as the velocity approaches the speed of light. So a couple of things I just want to point out here. Notice in the example that we used before, John and Luke were measuring the length of this train as it rushes past. Notice that Luke is the one who measures the proper length of the train. So in our previous example, or in the example we used to develop this formula, it was Luke who measured the so-called proper length of the train, because he is at rest relative to the train. But it was John who measured the proper time between the two events that allowed them to measure the length of the train. So John measured the proper time that is delta t naught, between the passing, or between the events that allowed him to measure the length of the train. Right? Think about the two events that allowed him to measure the length of the train. It was the moment at which the front of the train passed him. That would be event 1, and it would be happening right here in his coordinate system. And event 2 would be when the back of the train passes him. Those two events are happening at the same spatial location according to John, so he measures delta t naught, or the proper time. And from that, he was able to measure the length of the train. But it is Luke who is measuring L naught, the proper length of the train. So you shouldn't be thinking in your mind that somehow one of them is measuring both the proper length and the proper time, and so that's the proper measurement. That's not at all how you should interpret this. Rather, one of them measures the proper length, the other measures the proper time between events to measure the length. In any case, that's the first example that I'd like to go through, and these are the general formulas that relate the length measurements by observers who are in motion to one another. These are very important formulas, and you should learn these formulas. And I think the formula is a fairly simple formula. The hard part is deciding what to plug in for the various numbers, specifically deciding who is measuring the proper length and who is not measuring the proper length. In our next example, why don't I stop there? In the next example, I'm going to do a little bit more involved problem that involves a spaceship traveling at a certain high speed between Earth and a distant star, Alpha Centauri.